All right, here are some examples. This is on page 20 of your notes. So we'll go through these and hopefully they'll help you with some problems. Okay, so the first one, for example, at the start of this section, so when we're talking about the box and the coefficient of static friction, okay, we want to calculate the coefficients of static friction and kinetic friction. Okay, so first, again, our formulas for static friction, okay, our force of static friction, force of friction static, we'll write it up, okay, is equal to the coefficient static friction times Fn. And then force of kinetic friction is equal to coefficient of kinetic friction times Fn. So in order to find either of these, we first have to find our Fn. So again, Fn for our box, we have our force due to gravity because it's on a horizontal surface is equal and opposite of Fn. So Fn really is just going to be equal to the magnitude of mass times gravity. Our mass is 45 kilograms times 9.81 meters per second squared. So our Fn is equal to 441.45 newtons. Then we just have to look back to find our force of static friction. And when we rearrange the formula, so for the coefficient of static friction, it's going to be the force of static friction over Fn. Looking back on page 16, our force of static friction is 100 newtons. We need more than 100 newtons to start moving. Divide that by our force of our normal force, 441.45 newtons, and our force of static friction we get is 0.227, okay, which is correct as we have it down here. Okay, and our force or our coefficient of kinetic friction is going to be our force of friction kinetic over our normal force. We look back on those pages, we can find our force of friction kinetic is 62.5 newtons. This has the same normal force. And we got 0.142 as our coefficient of kinetic friction. Okay. For this next one, calculate the coefficient of static friction for a box on the board in question 6A above. Okay, remember that the book begins the slide when the angle reaches 28.5 degrees. So I wrote down, I have our free body diagram drawn here showing our different forces. Okay, from question 6C, I wrote down our force of friction static max that we found, 5.96. So again, if I want to find our coefficient of friction static, I'm using this same formula. So it's equal to our force of friction static max over our normal force. So we have to find our normal force. I drew out this little triangle to help us with that. So this is 28.5 degrees. So we're going to go the cos 28.5 degrees. It's going to equal our normal force over our force due to gravity, which our Fg we're given earlier in the question is equal to 12.5. So we got our Fn is equal to 12.5 times cos of 28 degrees. So our normal force is equal to 10.985. Put those numbers in here. So 5.96 newtons over 10.95 newtons. And we got our coefficient of static friction is equal to 0.543. Question 7, or for question 10, we're going to use question 17 on page 6 of our notes. Okay, it has to do with the skier, so if you can look back in the video or just look back in your notes if you took them. Okay, so assuming the force found in part B was the maximum force of friction, what is the coefficient of static friction? So we found the with the skier, their maximum, or their force of static, or the friction static max is equal to, so again, this is looking back on page 6, that is equal to 2.7 times 10 to the 2 newtons. And then our Fn, which we also found back on that page, is equal to 6.1 times 10 to the 2 newtons. We rearrange our formula the same as this one. We get our coefficient of static friction. It's equal to 2.7 times 10 to the 2 divided by 6.1 times 10 to the 2 newtons. And we get 0.44. Okay, close. This one, they probably just didn't use the rounded values, they used the total number. The second skier on the same slope, he also attempts to pause, but because of the slope is quite icy, at that point, she accelerates down the slope. Her mass is 52 kilograms. If the ice reduces coefficient of kinetic friction to 0.1, what is the second skier's acceleration? So this is what our free body diagram should look like. We have force of gravity always pulling straight down, force of gravity parallel, that's what's actually pulling the skier down the slope. The force of friction kinetics, what's slowing the skier down a little bit, and then we have our normal force always going perpendicular with the surface. Here, angle, it says, if we look back at that question, we have 24 degrees from the parallel, or from the horizontal, so that would be the 24 degrees is there, making this angle 66 degrees. We draw our second triangle, FG on this side, Fn, this would be 66 degrees, and this would be our FG parallel, and we have our 90 degrees there. So now we can use this to solve for FG parallel. Well, we also need the FG. We'll need a couple different things. We eventually need to find our net force that's pulling her down, okay, which will be the FG minus our FK, and we can solve for that. So we'll start by, let's just find our force due to gravity. 52 kilograms times 9.81 meters per second squared. And our force of gravity is 510 newtons. From that, we can now solve for our force of gravity parallel. Okay, by going cos 66 is equal to FG parallel over FG. So we got our force of gravity parallel is equal to 510 times cos of 66, which is equal to 207.44 newtons. Okay, from there, we need to find our Fn. So that's going to be basically the same as this using sine, so 510 sine of 66. So Fn is equal to 465.9 newtons. Once we have our Fm, we can find out what our force of friction is because we're given the coefficient of friction. So force of friction kinetic is equal to 465.9 newtons times 0.10, and our force of friction kinetic we get is then 46.6 newtons. So our F net is going to be our force of friction, or our force due to gravity parallel to the slope, so our 207 minus the force of friction pulling us up, so 207.44 newtons minus 46.6 newtons. Our F net is equal to 160.8 newtons. Okay, now F net equals mass times acceleration, so acceleration will equal F net over mass, 160.8 newtons divided by 52 kilograms. And we get our acceleration is 3.1 meters per second squared, which is equal to this.